All right. So hopefully this is just review. Hopefully that was relatively easy. Capital dark shell, so that's our dominant allele. That means if I have a capital letter, if I have a dominant allele show, it's going to show a dark shell color. Lowercase d, light shell color, so that means you have to have two lowercase letters in order to see that recessive trait. Use a Punnett square to determine the probability of a light-shelled roly-poly from two heterozygous dark parents. So heterozygous means different, so I got one of each. Capital D, is that one going to be light?
No.
Capital D, lowercase d, is that one going to be light? Capital D, lowercase d, is that one going to be light? Lowercase d, is that one going to be light? Okay, so 1 out of 4 are going to be light shelled, and we're leaving it as a fraction for this for right now. Now, keep in mind that depending on what the question is asking, you might have to convert that to a percentage. All right, Punnett square to show the probability of a dark-shelled roly-poly from a homozygous dark parent mated with a homozygous light parent. So, homozygous dark, homozygous means the same, homozygous light, homozygous means the same. I know every single one of them are going to be capital D, lowercase d. So we want the probability of a dark-shelled roly-poly. All 4 of them are dark. Out of 4, that gives us a 1, which is fine too. But leaving it in the fraction form is 4 out of 4. If you went ahead and put it as a 1, it's okay.
I just put 1 over 1. Put it 100%.
Oh, okay, yeah, we don't want a percent, but it wouldn't be 1 over 1 because we have 4 individuals. So now, did you go 4 over 4 and simplify 1 over 1?
Yeah.
Okay, same difference then. All right, I got you. I see what you're saying. Okay. All right, so number 3.
Yeah, I wrote it on there. I said 4 equals 1 over 1.
Okay, that's fine, just so long as you know where it's coming from. Okay, capital S equals 1 shell stripe, lowercase s equals 4 shell stripes. Punnett square to show the offspring of a heterozygous parent and a 4 shell stripe parent. So 4 shell stripes is lowercase, so that means I have to have lowercase. Heterozygous means I've got 1 of each. Remember, you need to make sure that we can tell your capital from lowercase apart. So I've got heterozygous, I've got homozygous or 4 shell, capital lowercase, and this one all they're asking you to do is to show it. Okay, so that's a lot more practice over homozygous, heterozygous, and make sure that you understand those things. But like I mentioned, I think I mentioned that yesterday, the fact is that traits, I mean, a critter doesn't have just one characteristic. We have gazillions of characteristics, and a lot of times the characteristics that we have, they're actually controlled by multiple genes. So when we say hair color, there's actually more than one gene that controls our hair color. When we say height, you're not just tall or short. We've got multiple heights ranging from everywhere, and so there's multiple genes that control that. We're not going to go quite that far. Just keep that in the back of your mind. But we are going to start looking at dihybrid. So di means 2. So we're looking at characteristics 2 at a time. So this is a dihybrid characteristic here. Shell color and striping are on different genes. So light shell, 4 stripes. Heterozygous dark roly-poly with 4 stripes, dark, heterozygous, 4 stripes. So you're writing the genotype for each of those. So a roly-poly heterozygous for both traits. Heterozygous means different, so we need it to be different for both traits, but it's written all together. So we're not separating these things out. So these 2 letters right here still indicate one trait. It indicates shell color, but we still need 2 letters. 1 letter came from dad roly-poly, 1 letter came from mom roly-poly. This is still for the trait for shell color. We still need 2 letters. 1 came from mom, 1 came from dad. So we're still writing 2 letters for each trait. But there's 4 letters that represent 2 traits. Different traits usually have different letters associated with them. Homozygous dark with 1 stripe. So homozygous dark, I have to be this because it has to be homozygous, so homozygous means the same. With 1 stripe. Okay, is this the only way that I can write 1 stripe? What's another way that I can write 1 stripe?
2 capital letters.
Make sense? Okay, so understand also that based on what they tell you, there might be additional options for genotypes. You got to keep that in mind because that affects your probability. If you leave this out and just say that, then it will affect your answer. So you always got to be thinking, well, is there another possible way that I can show this genotype? All right. So before we move on to anything else, so this is kind of what we've been doing. Oops, I guess I don't need that yet. This is kind of what we've been doing. We've been taking one characteristic in a Punnett square and another characteristic in a Punnett square. But the thing is that now that we know how to write dihybrid traits, what if we are crossing critters that have, and we're taking into consideration both traits at the same time. So laws of probability can help us with this if these chromosomes are independently assorting. These traits are independently assorting. That means they're on different chromosomes. So when I look at my capital T, lowercase t, oops, I can move up, I think, yes. Capital B, capital B. When I look at this individual, that tells me that they got a capital T from one of their parents. This is my chromosome. How many chromatids does my chromosome have? Okay, they are sister chromatids. They're bonded at the centromere. Sister chromatids. Chromatid means a duplicate or a copy. So this chromosome, it has 2 chromatids, 2 copies on it. They got capital T from mom. But we also got lowercase t. So let's say we got lowercase t from dad. Same difference. This chromosome has 2 chromatids. By the time we get to mitosis or meiosis, we've already had the S phase happen. We've already had synthesis. We've already duplicated our DNA. So by the time we get to cell division, replication has happened long ago in interphase. All right? Now notice, oh, wait. Okay, let's do this. But we have another characteristic here. So we have the B's. So dad gave capital B. Mom gave capital B. Does this chromosome have the same structure as this chromosome? Do they look the same? No, I did the best that I could. I made them different color, I made them different sizes. Does this chromosome have the same structure as this chromosome? Yeah, I made them the same color, I made them the same length. These chromosomes pair up. Does anybody remember what that pair is called? What's the word that means same? So, homologous. If you can get that far, I'm sure a reader is going to know what you're talking about. Homologous chromosomes, because they're pairs that are similar to each other. It would be the same chromosome, chromosome number 1. Got this chromosome number 1 from mom, this chromosome number 1 from dad, whatever. This is a homologous pair right here as well. So this one might have come from mom, that one might have come from dad. Independent assortment tells us that these chromosomes, when we throw them through meiosis, they can line up, they can arrange in any order. It doesn't have to be biggest to smallest. It could be smallest and biggest. It could be any size. It could be any arrangement. They're not going to line up chromosome number 1, chromosome number 2, chromosome. They're not going to do that. It's random chance how they line up together. So if this characteristic is on one chromosome and that characteristic is on another chromosome, they are going to independently assort. They are going to randomly end up in those 4 brand new cells that we have at the end of this. So when I go through meiosis, in metaphase 1, my homologous pairs line up. Then they go to opposite sides of the cell. Then in meiosis 2, these guys line up and they get pulled in anaphase to opposite sides of the cell. So I could have one cell that has capital. This one's going to have capital. The same thing's going to happen to these. They're going to get pulled apart, capital, lowercase. Independent assortment, how they end up in those new gametes. So we're kind of simplifying things, but remember, we have lots of different chromosomes, and so there's lots of different combinations. So when I look back up at this right here, For the Punnett squares, you would have to take that into consideration. You would have to consider every gamete that could form. So this capital T could go with that capital B right there. Or by some strange blah, 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 when we go back, maybe that capital T went with this capital B instead of that one. It could have sorted out so it went with that one. This lowercase t could have gone with this capital B, or it could have gone with that one. They're going to sort out independently and randomly. So the gametes that I could get from this, I could get capital T, capital B, where this capital T goes with that capital B, or I could get this capital T with that capital B. I can get this lowercase t with that B, or I can get this lowercase t with that B. That gives us the possibility of 4 gametes that could have sorted out with this. What if we've got capital T, lowercase t, capital B, lowercase b. Now we've got heterozygous. So this individual right here, that's my capital T's. That's my lowercase t's. Now I've got capital B's and lowercase b's. So maybe in meiosis 1, or in metaphase 1 of meiosis, maybe they line up like this, or maybe they line up like that, or maybe they line up like this, or maybe they line up like that. It's random how they come together. The only thing that's guaranteed, if you will, is the fact that the homologous pairs are going to come together. So it won't ever line up like this because these aren't homologous pairs. The ones that are homologous are going to be next to each other. That's really the only constant in this situation. So let's say this is how they line up. So anaphase 1, metaphase 2, anaphase 2, metaphase 2, anaphase 2. So I could have this situation. I could have capital B, lowercase t's, capital, or lowercase b, capital T. I could. But let's say they lined up like this. So metaphase 1 of meiosis, anaphase 1, metaphase 2. Now I've got the lowercase together and I've got the capital together. So they could line up like that. So in the first situation, I had 2 different possible gametes. Does that make sense? Now I have 2 different possible gametes. I either have the lowercases together and the capitals together. That's 2 different possibilities. Before, I had 2 different possibilities, capital B, lowercase t, lowercase b. I had 2. So in all, I have 4 different possible gametes from this. What that means is this T could go with this or with that. So I could have this gamete or I can have that gamete. I messed these up. This lowercase c can go with this or can go with that. So I can have this gamete or I can have that gamete. Then you put those all on the Punnett square. So before on the Punnett square, when we put a gamete on each side, now you have to put a gamete in each spot. We do have 2 letters now because we're looking at 2 characteristics. Before we only had 1, but it still holds true that 1 letter for a characteristic is in each spot. There's 2 letters because it's 2 different characteristics. What that ends up being is this mess right here. So these are all the gametes that I just talked about. Then you put all of these down one side because that's one parent. Then you put all of these across the other side because that's another parent. And then you fill it in. Has anybody ever done a dihybrid cross before? So they take a lot of time, right? They take a lot of time. And when you're on an AP biology test, time is not your friend. So we want to find ways that we can narrow that down. But if this is what you're comfortable with, I'm fine with that. I'm just saying that this is like old technology. We've got some new upgrade. We have the Punnett Square 10 coming along here. And I'm going to show you how to use that in just a minute. But the idea is so old technology, old ancient dinosaur technology, we'd run these Punnett squares, and then it would say, what's the probability that these two parents will have this offspring? So we want this offspring. After we fill it in, we go back and we look for those offspring. There's 4 of them out of 16 in all. That means we've got 1/4. 1/4, that's our probability. 1 out of 4, technically 4 out of 16, will end up having those characteristics that we have. But we can simplify this. We can take this and do it in a simpler way so that, is that the one I have on the back? Yes. We can do this in a simpler way so that it doesn't take as much time. And also, I think that there's less mistakes with it, because look at all the things you had to do right. You had to get the gametes right. You had to place them right. You have to fill it in right. You had to count it right. There's lots of things that you had to do. So these were our parents crossed with heterozygous for both. And we wanted to have offspring that looked like this. That's the offspring that we wanted to have. So we need to have offspring that has this and this. That's important. Sometimes we'll be looking at things, well, it can have either this or that. So and or are important. In this situation, because this is the specific critter that I want, I need this and that. So you look at each characteristic individually, because that's the easiest way to do. And like I said, in a certain amount of time, you're going to be looking at these Punnett squares, and I don't even need to redraw a Punnett square anymore because I've seen them so many times. So first, I'm going to look at the probability of the T characteristic, whatever that might be, tall, short, let's say. So these are my 2 parents. This parent, this parent. So if I run my Punnett square and I do those 2 parents, what's the probability that I'm going to get this offspring? Say it again. Yes, and I'm not even gonna simplify it that much. You see why I would say 2 out of 4? I mean, you can say 1/2, it's still gonna work. I'm just gonna keep it like that for right now. Does everybody see where I got that from? I did 1 characteristic at a time, and boy, man, they were really taking their time. I did 1 characteristic at a time. I ran a little Punnett square. I used the Punnett square to find the probability for that. And I want to find this. So now I do the same thing. These are the 2 parents, so that's what I have to use. So I've got capital, 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 lowercase. All right, so what's my probability for these guys? So we get 2/4 for both, but you see how it's different for each situation. Okay? So, and, we'll find out in just a second, and is always going to mean that we multiply, because I need this and that, so I'm going to multiply those 2 together. So if I take 2/4 and I multiply that times 2/4, I get what? All right, watch. I know, fractions. Multiply, you multiply straight across. Add, you add the numerators and keep the denominator. So we're going to be doing both of those things here. If it's and, we'll multiply. If it's or, we'll add. 4 out of 16, let's simplify that. Remember that number? So all the time it would have taken to figure out the gametes, to place the gametes, to write the Punnett square, to fill in the Punnett square, to add it up, to come to that number, I came to it a lot faster, and you can do it even faster once you've got all those Punnett squares memorized, and you don't even have to draw them. Same exact answer. This is a lot faster and a lot easier, especially when we get to the point to where it's not dihybrid. So what if you've got a cross that's crossed with something else? Good Lord, I don't even know how to set up a Punnett square for that. So laws of probability are what you'll have to do. So I would suggest, especially if you know how to do the 16 square one, do it like this now for even the easy ones. And you can check your work if you want to. But this, to me, is a waste of time at this point. Okay, so I have a worksheet that I'm going to give you that has all this on you, has that example on there. So it shows the 16 square. It shows how to use the laws of probability to find the exact same answer that we did on the other side. And I'm going to give that to you as a resource here in just a moment. First, I want you to take out your AP Bio lab notebook, take out your formula sheet.
So if and means multiplication, what does or mean?
Add. And we'll do some examples. All right, grab a different color highlighter than what you've used before and box in the spot that talks about the laws of probability. I would also suggest that you make note of the fact that or means we add and means we multiply. Or means that we add and means that we multiply. Okie doke. All right, let's go back to roly-poly worksheet. Let's do this first one together. Okay, so here are our parents. That's what we're going to cross. Probability of a roly-poly that's dark-shelled with 4 stripes. So the first thing that I always do with these is I look at these individually and I mark to see what the genotypes are to even see if the genotypes are possible. Okay, so we're going back to the other side where dark shell color, where was it at? Blah, 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 blah. Dark shell color is dominant and 1 stripe is dominant. Yes, because that was 4 stripes. So dark shell is dominant. 1 stripe is dominant. All right. That way I don't have to flip back and forth. Okay, so a roly-poly that is dark shelled. What's a possible genotype just for shell color where they come out dark shelled? Yep. Anything else? Okay. So now I take a look and I look at the parents. If these are the parents, is it possible that I have an offspring that would end up capital D lowercase d?
Yes.
Yes. Is it possible that I have an offspring that could be capital capital?
Yes.
Okay, both of those are possible. All right, 4 stripes. So what's a genotype for 4 stripes?
2 little s.
Has to be 2 lowercase. Nothing else. Looking at the parents, is it possible that I have would get an offspring that's 2 lowercase? Yes. Okay, so all of these are good. All right, now we need to find the probability of a roly-poly that's dark-shelled with 4 stripes. So I could have a dark-shelled with 4 stripes that looks like this, correct?
Yes.
Or I could have a roly-poly that's dark-shelled with 4 stripes that looks like this. Make sense? But keep in mind, I need this and this. I need this and this. So we have and or both coming into play. And means we, or means we Okay, so I know I'm going to add here, but I'm going to multiply whatever this is times whatever that is. Then I'm going to add it to whatever I multiplied this times that. Okay, so these are my two parents, and then you can always write out the Punnett squares if you need to. I've got two capitals. I've got capital, lowercase, capital, 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 lowercase, capital, 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 lowercase. What's the probability? What's the fraction for capital, lowercase? Okay. Then I'm just going to go ahead and do this one since I already have that Punnett square done. What's the probability for capital, capital? All right. So now I need a roly-poly with four stripes. So I have two heterozygous parents. I run through that. What's the probability for lowercase, lowercase? What's the probability for lowercase, lowercase? So in math, do I add or multiply first? Okay, so you need to multiply, then add. 2/4 times 1/4 is what?
No, 16.
Plus 2/4 times 1/4. What's 2/16 plus 2/16? Okay. Now we reduce. What does that reduce to? That's the probability. Hopefully you wrote it a little bit smaller than I did. Got what you need? I'm about to erase. I didn't erase that one because I know I'm going to need it. All right, probability of a roly-poly that's dark shelled with four stripes. Does that sound familiar?
No.
Doesn't? Now does it sound familiar? Yeah. Okay. So, is it the exact same problem? What's different then? Okay, so be careful. This time we've got different parents. All right. So we already did this part though. Let's see if that still applies. If I've got heterozygous parents, could I have an offspring that's capital lowercase? Yep. Could I have one that's capital capital? If I had heterozygous parents, could I have offspring that's lowercase s, lowercase s? Okay, good. So I know that that still applies. Dark shelled with four stripes, we already found out that it's going to be capital D, lowercase s, or, which means plus, capital D, oh, I'm sorry, capital D, lowercase s. That's what we did before, right? Oh, wait, I'm doing it wrong already. No, I'm not. Because capital S was one stripe. Yes? Fact checkers out there? That was what we had before, right? Yeah. Okay, good. Okie doke. So, for these guys right here, I already have this Punnett square, so if you drew it out, why not just use that one? But I need a Punnett square that's heterozygous for my D's. If you need to, then go ahead, but I don't even need to because it's basically going to be the same as this with just different letters. But if you need to, by all means, go ahead and do your Punnett square. But chances are you're going to get to be doing them so much. Okay, so I need this and this, or this and that. What's the probability of capital capital? What's the probability of capital D, lowercase d? What was the probability of lowercase s, and lowercase s, lowercase s? All right, so in math, do I add or multiply first? Okay, so 1/4 times 1/4 is what? 1 times 1, 4 times 4. Plus, what's 2/4 times 1/4? What's 1/16 plus 2/16? So that's the reason why I actually leave it instead of putting this as 1/2. I mean, technically you can, but think about what that would have been. I would have 1/2 times 1/4, which would have given me 1/8, and I need to add 1/8 and 1/16, so I would have had to go ahead and convert that so I can multiply it. 1 times 2 gives me 2, 2 times 8 gives me, I would have to done an extra step. So by simply leaving it in its unsimplified form up here, I don't have to do more work later on. Because if I get to the end and I have 4/16, then I can simplify it then. But if I get to the end and I have 3/16, well, that's my answer. And I'm done. Make sense? All right, I want you to go ahead and do the next 2 problems. Go ahead and do the next 2 problems. And like I said, baby steps, do it the same way that we did it before. Start with figuring out what the genotypes would be. Double check to make sure the parents that they are giving you make that possible. Then go through, do your fractions for probability. All right, so our answers for the next 2. Okay, I gave you the sheet that has the example on it that I was just talking about and going through homologous chromosomes, homologous pairs, looking at the 16 square Punnett square, comparing using the laws of probability to the 16 square Punnett square. So AP Biology notebook, open up to where we put the little foldable at. So the worksheet I gave you with the examples plus this would be really good resources right next to that sheet. So if you've got your sheet taped in, I think I said the right-hand side, just turn to the next 2 pages and tape those guys in. Turn them sideways, couple pieces of tape at the top, couple pieces of tape on the top on the other side, fold it in. So you turn it sideways, couple pieces of tape, and then fold it in. So there's a couple different ways that we can take what you've done today one direction we can go is instead of just a dihybrid cross, we add more characteristics and find what's the probability of an offspring. We'll be doing some examples and some problems with that. The other direction we can take this stuff is you already know that with a monohybrid cross, you can apply chi-squared data. The dihybrid, you can also do the same thing. So your expected is still going to come from Punnett squares from what you expect. Your observed is still going to come from the data, the numbers that are counted. So go back to your foldable because the ratios are going to be probably even more helpful with dihybrid stuff. I would expect, and a lot of hope too, that these are the three most common ones that would be on an AP biology test that you would need to like memorize what the ratio would be for it. So once again, I've done it the same way. So blue ink tells us that that's the genotypic ratio you're going to get when you run your 16 square Punnett square. Red ink, that's the genotypic ratio you're going to get. Black ink, that's the genotypic ratio you're going to get when you run the Punnett square. I don't see this a whole lot. I mean, I do see it in some problems, but I don't see it a whole lot. Phenotypic ratio, I see a lot. The dihybrid cross, 9 to 3 to 3 to 1, that should be like burned into your brain. Dihybrid, when I have heterozygous for both characteristics, it will always be a 9 to 3 to 3 to 1 phenotypic ratio. So I'll have 9 of my dominant allele showing up, 3 with dominant for one, recessive for the other, dominant for the other, recessive for one, and 1 that's all recessive. 9 to 3 to 3 to 1, that's super common. It should be burned into your brain. Then I think the other two, this one is pretty easy. Why is it that this will always be all the same phenotype when we run this through? Because it's, say that again. Oh, why will I never have a recessive trait show up at all? Right. This parent has recessive alleles that they pass on, but this parent doesn't. I will never see a recessive phenotype showing up when I have these two parents. So that should be a really easy phenotypic ratio to spot, just simply because you don't have to do any work for that. It's always going to be dominant. They'll all be the same. This one's easy because when you look at the parents, both parents are heterozygous for both traits. 2 dihybrid parents with heterozygous for both traits, 9 to 3 to 3 to 1. So the other one should be relatively easy because it's kind of like the first one. So whenever I have a heterozygous for both traits crossed with homozygous recessive, that's always a 1 to 1 to 1 to 1 ratio. I will see equal number of dominant alleles, equal number of dominant of one characteristic, recessive the other, equal number of dominant of this one, recessive of that one, equal number of all recessive. So those 3 would be ones that you would need to memorize. I think that I'm hoping that we'd be safe with just those 3. The other 2 I don't know any tricks for, I'm sorry. These are the ones that I see most commonly, and they're easier to see the ratio because you can just look at it. So grab your highlighters and match up your ratios for your phenotypics characteristics to the crosses. Okay, so that's what I have for you for today. So the rest of the time that you have, you can work on make sure that you get your host a competition. If you're not competing, make sure you comment that you're not competing at all, but I would recommend at least a test. AP Bio packet that I gave you, and so now that first page, the back side of the first page, that Punnett square that is at the bottom, that's a 16 square Punnett square. So that's similar to what I talked about on the first thing. They're doing dihybrid characteristics. So each one of those spots is going to have 2 letters in it, but they have to be 1 letter of the one characteristic and 1 letter of the other characteristic. So you have to go and look to see what the gametes would be, then fill that stuff in. So look back to that Punnett Square that I gave you to get that information. All right, next week. So here's what I know about next week. Tuesday of next week, we have a guest speaker. Wednesday of next week, we're meeting with Biomed 1 in Miss Newman's room. Have they talked to you anything about our HOSA get-together? They haven't said anything about that? Because we usually, like, bring stuff. I don't know. Let me text Mrs. Newman because I'm surprised they hadn't come talk to you about that. But then, like, everybody brings like a snack or something for our little get together,
Like we make something
or buy something.
I'll bring some.
Well, hold on. Before we start deciding that, let me find out what's going on because I'm not the deciding factor in it. Maybe they've got everything set up. I don't know. Friday, I know I've got a movie. Monday, I know we've got stuff related to laws of probability and chi-squared stuff, and it's like your first classwork grade, so nice, easy classwork grade, and it will help you for stuff going on. And then Thursday's kind of up in the air because I don't know if KTC is doing something or not, so we'll find that out on Thursday. But I do know Tuesday guest speaker, Wednesday with Biomed 1 for our hosted get together, Friday Biomed related movie. Of course, it's good movies, and 2 of them if we have time. Huh? I'm not gonna tell you that because it's more fun to be a surprise. No, it's not. Oh, good Lord, no, it's not.